Hello and welcome to the second part of our special Movers and Shakers interview with Chris Williams, who is Artistic Professor of Architecture and Civil Engineering at Chalmers University of Technology. For those that haven't yet had the opportunity to see part one of Chris's interview, it is available to watch on our conference YouTube channel. For now though, we rejoin with Chris and his Your Space, Your Structure presentation.
Now, this is actually perhaps a bit more relevant to shell theory now, because we've now got a surface. And surfaces are in some ways simpler than 3D, in some ways more complicated. But you've got your coordinate curves on the surface. So you replace your coordinate surfaces with coordinate curves lying on the surface of your shell structure. And this equation here is what you use if you wanted to calculate the distance ds between 2 points. So between these 2 points, the coordinates, which are sometimes called x with superscripts or theta with superscripts, as they change, you move, and this equation gives you the distance between those points. Those of you who do lots of stuff with Rhino and computer programs like that will be used to using u and v as your surface parameters when you're describing a surface. But it's much better to actually use things with superscripts, even though it's confusing to begin with. These things, the G's, are what's called the components of the metric tensor. And those enable you to do this calculation of distance. This formula, even though it doesn't look like it, is actually very much the same as the cosine rule that you're used to using instead of Pythagoras. So you know, with a right angle triangle, you use Pythagoras' theorem. With a triangle that's not right angle, you use the cosine rule. And this equation here is effectively the cosine rule. Now, the nice thing about this is that not only does this allow you to calculate the distance between these 2 points, this point and this point, it also allows you to talk about strain, because what strain is a change in the distance between 2 points. So if you know how all the distances change between different points on the surface, then you know everything there is to know about the deformation of the surface. So if you understand this stuff about these G's, then you can immediately have a very simple explanation of what strain is. It's much more difficult trying to describe strain in, say, Cartesian coordinates, because you have the fixed coordinates, if you like, and then you have your material moving past the coordinates. And it's an incredibly messy way of looking at it. Whereas looking at it this way, with your coordinates being dragged with the material, everything is straightforward, except for the fact that you've got these rather annoying subscripts and superscripts. Here, in this bit here, there's a sigma I equals 1 to 2, j equals 1 to 2. And that's used all the time in tensor analysis. It's the Einstein summation convention. Okay, so I won't talk about this in any detail, except to say that probably some of it is familiar to you or to some of you. So, for example, these are the equations of equilibrium of a two-dimensional continuum with no load. So you've just got stresses within the material, but you haven't got any gravity or anything in it. Now, this sort of thing, well, I learned this when I was a student, and I used to teach it when I was at Bath. But it's quite possible that some of you, particularly in the UK, will have managed to complete your engineering education without ever seeing these equations. I don't know. We could have a long discussion about how much of this stuff you should have, if any, in an engineering course. So sigma x, you're probably familiar with. Tor xy and tor yx, which are equal, that's this equation here, through complementary shear stresses. And basically, this equation tells us how the stresses can vary within a material in order to maintain equilibrium. So this is in Cartesian coordinates. This here is in curvilinear coordinates. And you can see immediately that the equation is much shorter because it uses the summation convention, which we just mentioned. It also applies in 3 dimensions as well as in 2 dimensions. And actually, it also applies in 4 dimensions of relativity. And in relativity theory, shows that that equation, the equilibrium equation, is actually a geometrical property of space-time. But we're getting a bit away from ourselves. It's also nice to be able to write equations without a coordinate system, because in real life, you don't have a coordinate system. So if you say, well, in order to write down equations, I have to imagine a coordinate system, that seems a bit sort of, a bit dumb, really, a bit inelegant. And so this equation, these here, the sigma equals sigma t means that the stress tensor is the same as its transpose, and that's the complementary shear strain. Shear stresses are equal. So all these equations here are saying the same thing. And then those of you who know a little bit about elasticity will know that in 2 dimensions, you can satisfy those equations by introducing phi, which is the area stress function. And again, you can write that down in different ways. The stress function, area stress function, is used quite a lot in shell theory, where what you do is you use this 2-dimensional analysis in plan. So you look down on your shell structure, and what you see is a 2-dimensional structure in equilibrium in a horizontal direction. And all these equations remain unchanged. Well, the equilibrium equations remain unchanged. The other ones do change. And then what you do is to say, well, actually, I've got a curved shell structure, and you then use the area stress function together with the height of the shell, the variation in the height of the shell, to give you the equilibrium equation in the z direction. Anyway, sticking with 2 dimensions, we then have these relationships here between the displacements u and v, or in this case here, u1 and u2, and the strains. This is the direct strain, tensile strain, and this is the shear strain. And these 3 equations are summarized by this one equation in tensor analysis. What happens here is that the half is quite interesting, because this definition definition gives the same result as this one and this one, because you basically get half of something plus the same thing. So you lose the half. What happens here is that there's actually not so much a mistake, but it's a bit of a mistake. There really ought to be a half in here, but there isn't. I don't know whether you will be aware of more circles for strain. You're probably aware of more circles for stress, but there's also more circle for strain. And in more circle for strain, you have to put a half in front of the shear strain. And the reason for that is because whoever decided to define shear strain in this way should have left the half out. It's rather annoying, really, because it means that both the shear modulus and elasticity and also the viscosity in fluid mechanics have got a rather annoying lack of a half there. Anyway, not to worry about that. We then have constitutive equations which relate strains to stresses. And again, they become simpler here if you use the tensor notation. And this equation, the tensor notation here, applies in both 3 dimensions and 2 dimensions. Whereas if you use the Cartesian notation, it gets very messy in 3 dimensions because you've got 6 components of 6 components of stress and 6 components of strain. And then you can also write them here if you want to be a bit more elegant without using any coordinate system. So what we have here is things like stress here is a tensor, which is an extension of a vector, if you like. So you start off with scalars, and then you have vectors, and then you have higher order tensors. So stress is a second order tensor. Vectors like force are first order tensors, and scalars like density are 0th order tensors. Anyway, so you have these compatibility equations, you have constitutive equations, compatibility equations, and when you combine them, from the compatibility equations, you get this. Then you can put this into there, and you finally end up with one differential equation for the stress function, which you can write in this notation, or this notation, or this notation. The nice thing about this equation, the biharmonic equation, is that it's the same equation that you get in plate bending. So you can get quite a lot of understanding about stresses in 2D from plate bending. And this picture here is just an example of the stresses that you get around a circular hole, where essentially what you have to do is to solve this equation, biharmonic equation, in polar coordinates. And you probably, if you want to do that, you probably do best to look at Timoshenko theory of elasticity, which is the classic book on, if you like, conventional non-tensor elasticity theory. Right, so that is the end of my talk.
Chris, thanks very much for taking us through your presentation there. Very interesting insight to some of your work in the field of spatial structures. We're now going to move to the final section of our interview, which looks at the future of spatial structures, and in particular the 2021 conference. A key theme of the Spatial Structures 2021 conference is inspiring the next generation. And I wondered, what advice would you offer to aspiring engineers looking to enter the field of spatial structures?
Right, okay. Well, I think it's always difficult to give advice. I suppose what I would say is that it's very important to have a long view, which doesn't just mean the last 10 years, it means the last 20 years, the last 50 years. And of course, I think for all of us, you look back to the builders of cathedrals and churches and masonry bridges, as I suppose being the most inspiring structures. And I think nothing that we've produced in the last few years or in my lifetime compares in any way with the Gothic cathedrals that our ancestors built. And there's a very good lecture actually, which somewhere on YouTube by Jacques Hyman about stone vaults. And I think that is always the starting point. From a geometrical point of view, of course, there is the science of stereotomy, which used to be taught to engineers and architects, particularly in France. And it's the science of cutting stones in order to make vaults and arches and so on. So all the sort of latest software is just, if you like, a continuation of a long history. The other thing I would say is that you also want to look for examples of shell structures in nature and all around you in everyday objects. So I mentioned the sieve, for example, in terms of the grid shell, but if you take something like this glasses case, then this is a shell structure. And by pressing it, you can feel that it's quite stiff in some parts, quite flexible in others. And so in these everyday objects, tin cans, cutlery, you name it, obviously things like car bodies, they're all shell structures. And I suppose something we haven't touched on, something which is very important, is the fact that the structure has to have some application. So I was lucky enough to do some work on the Millennium Dome, and which was built, of course, for the Millennium, but then it was pretty much a white elephant, and nobody knew what to do with it, and there was a big fuss about it. But then somebody had the idea of building the O2 arena inside. So that building had, if you like, a second life, and that was good. The big problem with the Mannheim shell is that there's no obvious use for it, given where it is in the outskirts of a relatively small industrial city in Germany. So I think it's partly a technical issue. You want to design good and beautiful and long-lasting structures, but it's very important that the structure should have some meaningful use for people. And obviously, it's nice if it's a public building. So if you're really lucky, as I was with the Great Court, for example, is you get involved with a public building, which is then something for future generations to enjoy. I think for all engineers, it's very good if you're lucky enough to have a wide range of experience. So you might work on shells, but if you're lucky, you work on bridges, other sorts of buildings. But very often it's a question of luck, really, being lucky in the people that you happen to be working with.
That makes complete sense, Chris. We've run out of time for our interview, but
Okay.
I would like to thank you very much for taking us through your presentation today. It was very, very interesting and a fascinating insight into the work you've been doing across a number of projects. For our guests watching this interview, don't forget to follow the 2021 conference on social media. Links to our accounts across social channels are included in the description section of this video. Chris, once again, thank you very much for joining us today on the Movers and Shakers interview series. It was a pleasure to speak to you, and hopefully we can catch up with you again as we move closer to the 2021 conference.
Okay, certainly. Right, good.
Thanks, Chris. All the best for now, and speak to you soon.
Okay, thank you, Mark.